Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Kirk Gray.
And this is Fred Schenkelberg. Hey, Kirk.
Hey, Fred.
You talk about you got to test a failure all the time, right? You have to have failures.
You have to test
learn
to a
anything.
limit. Yes, you have to test to a limit. It may not be a catastrophic destruction of your product. And in fact, I wouldn't go beyond operating limit in most cases, in only special cases where I'd go beyond where you can't see it operate.
Right. Well, you've often said, though, that a failure of any kind is gold, whether it's in the field or in a prototype or whatever. That's when you actually can learn something.
That's right.
Now, here's the dilemma is, and it comes from, I got a sneak peek at this database that Karina is putting together, and I'm drawing a complete blank on her last name, so I apologize. But she's in the maintenance, like factory maintenance type world. And so, and she showed me one setup for, I think it was a gearbox of some sort. And it was focusing, the example I saw was focusing on just gears, right?
Gears,
a gear of some sort.
A gear that has a wear out mechanism, yes.
Well, it doesn't have just one. It has many.
No, very, very many.
But so she said, she pulled up a screen and it had like the four most common failure mechanisms. And one of them was a bending force on the tooth that creates a crack and then eventually it falls off. Right. And another one was it's wearing. At the top of it is wearing. You get these metal filings everywhere. Kind of the different signature is the way she called it. And it's a good term for it. Is one you can see a crack, the other one you see this wear pattern.
Right.
And then she went on a couple other mechanisms. And then what was cool about it is then it said, oh, and once you see this and at different stages, she had it broken down by, this is very early indicator that this is happening. Right. And if you don't treat it, it's going to look like this. And if you don't replace it, it's going to look like this. And eventually it's just going to fall apart. Here's the type of symptoms you're going to get. And so I thought, this is really cool because immediately for me, it said, oh, here's 4 ways that this tooth can fail on one screen with pictures. And I thought it was pretty slick.
Right. And there are different factors that
cause those
will
things.
Impact that. Right. Temperature cycling.
It could be thermal cycling.
Lubricant.
It could be lubricant failing. It could be misalignment. It could be designed improperly. All kinds of stuff.
Imbalance. All kinds of things. Right.
They go into it. And I was like, but usually when we're doing failure analysis, we look at it, and if you're not familiar with the wear pattern, say on the edge of a tooth, that's not normal. If you don't know what normal looks like, every tooth you ever took apart, every gearbox you took apart, it always had some wear pattern in it.
Right.
You would think that's the way it's supposed to look. Right. And so part of it, and I ran into this a handful of times by experience where, like white powder on a circuit board, right? Yeah, I'm sure you've run into like the board failed, there's white powder on the, like, well, what is the white powder? And so your hands contain different like chlorine, and other ionic type chemicals that can cause metals to move and cause short circuits and stuff like that. And but until I ran into one of those and started asking around, I had no idea what it was. And so then I became very suspicious of white powder and said, well, the first step is go do this, figure out what is this white powder and is it benign or not? And where did it come from? Stuff like that.
Right.
But we do that all the time. I remember the story, and I got to find that episode and link to it, is that you were over the shoulder of some poor electrician diagnosing some circuit breaker in your house and or whatever it was, or your furnace or some system.
Yeah.
But you could see that's the problem. And he goes, okay, I'm replacing the whole board.
Well, I don't recall that, but you know,
Yeah.
it's the fact that yeah, you have to know something about failure mechanisms, and the way you do that is you have to actually look at actual product that's come back from the field or failed,
Well,
and
what's a
that's
better way to do that? How do you, because we all don't have 30 years to get experience with all the failure mechanisms the hard way.
no, we don't have 30 years, and certainly, but if you're in a company, you can look at a lot of the failure. If it's been doing failure analysis, you can certainly look into that, and they're all very specific to your industry, whatever it is. If you're
Yeah.
making pumps and motors, then the wear mechanisms and monitoring those wear mechanisms, and there are many different ways you could measure the density of the oil or the lubricants, or you could look at the content of metal in the lubricant, or there's
Hmm.
just it's
But
kind of
this is
going
all
along
coming from experience here, Kirk. This is all coming from your experience and
it's
knowing,
coming
you
from my
know,
experience, right?
yeah,
But also knowing material science and physics.
yeah, you have to understand some of the basics of it. And for me, it's always been what I like about doing failure analysis. It is an opportunity to go learn something and always approach it with, well, that doesn't look quite right. And then I changed it to, why does it look that way?
Right,
Why is it behaving that way? And then
right.
we go into more complicated, like fishbone diagrams and stuff, and brainstorm
Mm-hmm.
what could be happening.
Mm-hmm.
And I've also seen databases with like FMEAs where they say, oh, if you have a capacitor, it could fail short, it could fail open, or it could be intermittent. I says, well, that's not useful at all. I
No,
mean, come on, tell me
no,
something useful here.
that's right.
Those are symptoms of an underlying problem.
Right,
What is the mechanism? Why is it open or short or
right.
intermittent? How in the world do you get it intermittent on a capacitor? It's probably where it's not, solder is
Yes.
cracked all the way through and it's bouncing up
Yeah,
and down with
yeah.
temperature.
Definitely capacitors are one of the hardest things to diagnose and open, except for a short. If you can do it with a
Shorts are
short, but
easy because it's just
yeah,
this,
it's always open. Yeah.
it behaves like it's open, but if it's supposed to give you a capacitance
Right.
value
If the
there, some
right,
circuits then just don't work,
right,
even though it looks like it's fine. But you take it apart and you say, oh, okay, well, this lead came apart. This, the foil is whatever. There's ways to do it, but you have to know what you're looking for. And
right,
we're a really good failure analysis lab, the technicians and the engineers that work at really good labs, they remind me of the old mechanic that could lean up against a Jeep in the army and go, oh, your timing's off. They could just feel it in,
right.
in the
And that came
vibration.
from experience.
Yeah.
That came from looking at and knowing in the past. And I think this is where AI is really going to help us. I mean, it can look through thousands of records of the field data and then show rates of failure. Especially for things the problem like with that analysis is you're talking about variabilities of end use conditions that may have caused a failure and
Oh,
wear
yeah.
out.
And just different ways
But
we
but
describe stuff.
but when we talk about the electrolyte in the aluminum electrolytic capacitors, uh, getting a wrong formula, somebody starting and having a manufacturing uh, excursion, as we would call it, where they manufactured and didn't know it, um, eh, nobody counted on the electrolyte being mismanufactured.
Well, yeah, we often trust our vendors and suppliers and our
Exactly.
own
We have to.
manufacturing to get it
Right.
right. We don't have time to double check we never be able to sell a product. But the
Right.
idea is that when you're doing failure analysis at any
Hmm.
stage, I contend that there's, you talked about the chemistry, physics, and just how could this
What
occur?
drives that? What
Yeah,
is
what's
driving
driving
these?
this?
What are the
Just
inputs? What are the like you say, maybe just putting it together. What are the things? What are you listing the different parametrics that cause it? to
Yeah. Now,
happen.
if you
And
ask a college grad coming into, reliability engineering, they may or may not have taken a class on failure mechanisms. They may or may not be familiar with electronics at all. They might have been in a mechanical system,
I
right?
don't know where there's a class on failure mechanisms.
There's one at Maryland. It's actually really
Okay.
horrible, by the way. I've heard it from many students that it was a painful process.
Yes.
It was
Okay.
not a good course. It and the professor, didn't care.
Okay. Where's a good failure
I don't know.
course?
That's the only
Yeah,
one I've heard of.
that's what I because they have to dig from people's the real. Okay. There's
But anyway,
just
so
like you talk.
but
Okay. Go
let's
ahead.
say you get a new mechanical engineer joins your team and they're going to be working on a circuit board. My question to them is how many ways can corrosion occur on a circuit board? And if they get a blank stare, is that you need to go learn it because there's galvanic corrosion, there's oxidation type corrosion, there's this and this and this and this. There's like a dozen different electromigration type stuff,
Yeah.
on and on and on. I'm drawing a blank here as I'm trying to
And then
think
you
out
work
loud.
on a 200 kilovolt linear particle accelerator, and you find out that the absolute 999.99999 purity water that has to run so that between the uh,
Acting like a
source where the
dielectric.
plasma source was and has to be an absolute pure 15 mega ohm, water
Hmm.
um, resistance. If you have a leak and it goes on a circuit board, guess what? You're going to have etching on the traces. Why? Because absolutely pure water has a certain pH that's not quite neutral. I think it actually is
Yep.
acidic, slightly acidic. So it would actually attack the metal ions.
Wow.
And, that was nobody would know that. Who uses absolute 15 mega
Well, I've
water?
seen people use really pure silver and on a board and say it's got great electrical properties. Yeah, it also draws its own circuitry. It'll go wherever there's electric magnetic field, it's going to follow it, independent of where
Yeah.
you put it on the board.
Well,
Or really, really pure tin, the
right.
tin
We got tin
pest.
whiskers. That's been the
No, not tin whiskers, but tin pest. You ever hear of that one?
tin what?
Pest, Pest.
PEST.
Yeah, so
No.
very pure tin. And I don't know if it had to be under current or under some kind of load. It just turns to powder. You might form it in like some metallic shape, but it with oxygen, it just turns to powder.
Oh, it oxidizes.
Yeah,
It oxidizes. Okay.
yeah. But
Well, you wouldn't use iron as a conductor either.
well, people
Trace.
have. They have for a long, long time. But the idea is I think if you're not inherently curious, like I took my mom's toaster apart and then she wanted me to put it back together, which I never did. So I learned a lot about failure mechanisms trying to put it back together.
Right.
But the idea is that it would be cool to have a workshop where you have a bunch of stuff and it's tossed away, or there's the uh, maker fairs where you can bring an old toaster that's not working or coffee pot or whatever device it is, and they have a whole bunch of people there that will diagnose it and say, "Oh, here, fix this or resolder a wire or do stuff like that."
Hmm.
But they get great experience going after one product after another and just doing quick analysis and repairs.
Right.
And
Right.
but it's how do you create awareness of I mean, if you didn't know about galvanic corrosion, and I saw this just the other day, they were putting two very dissimilar metals together. And I'm like, I got a little chart that talks about if you put copper with iron or something like that, they're really different. And they cause, just by being in contact with each other, will corrode. And they went, what? How's that? Yeah, here it
Isn't
is.
that what? Isn't that how you make a thermocouple too? Uh,
Yeah, kind of thing. It's like,
two different metals,
yeah,
have that interaction. Yeah, well, Fred, it's just the variety of industries that and the different. I mean, if you were in the down hole measurement industry for oil wells,
yeah.
that you're talking about a whole different world of a above 150 degrees C type
Well, in
failures. You
space,
know that,
there's no gravity, so heat does not rise. So yeah, you got to deal
right,
with heat a different way.
right. But I guess so. And if you're dealing with biomedical equipment, it's just there's some there's of course a lot of similarity with the failure mechanisms that occur on a PCB, a printed wiring circuit board assembly, and they in fact pulling out any PCB from from a system won't. They all look this. They look pretty much the same. A power supply
Yeah,
looks pretty much the same. So, yeah, there's some very common, you know, uh, failure mechanisms like component adjacency, touching, it's kind of those kind of things, but they're all unique in some ways to how the product's been designed and its environmental conditions and just a lot of things. So, and also manufacturing excursions, like we talked about, that
that always
are
throw a
not
wrench and stuff.
those are not expected, and
Well, they
they're
should
not
be.
really okay. What if all these component manufacturers? What if their epoxy was the wrong had the wrong thermal coefficient of expansion for their encapsulant?
It would just rip apart whatever's in it. Yeah.
Right,
Yeah.
exactly, and that's
But
not
I ran into
expected.
one on epoxy. I think you were at Dell at the time. I was at HP. Is that it was the black epoxy that we commonly use over
Yeah,
electronics, right?
right,
It has carbon black in it,
right, right.
and it's meant to be. And there's a flame retardant material in there that they have different techniques. And I don't know what was commonly used, but some of them create water. Some of the flame retardants, kind of explode and blow out the flame. There's a bunch of
Mm-hmm.
different techniques for flame retardant stuff, but
Mm-hmm.
there's like 20 to 30% of that epoxy blend is this flame retardant stuff. And it's the one that I ran into was pretty corrosive. So that if that particle got separated from the epoxy and it
Mm-hmm.
landed and they would land right on the leads of
Mm-hmm.
the primary, signal lead or something like that, timing lead, it'll corrode it and cause it to corrode open or short with the next system. And we
Okay.
discovered it because our disk drives were failing. And you start
Mm-hmm.
taking it apart and you're seeing this weird corrosion that the chemist guy said, well, this comes from the flame retardant in the epoxy. I'm like, what? And it turns out that the component manufacturer, the ones that package it, bought the epoxy, and the epoxy folks bought the flame retardant from somebody. And this is when we're off
Yeah,
air
it's a
and we're
long
talking.
chain. Right. It's a
Yeah,
long chain.
and they changed the mesh of sifting this material so that it was a
Right.
little bit bigger, and they got
Right.
more yield that way. So they were
Right.
happy, and they said that won't affect anybody. But if you add a little bit of vibration, and some of that epoxy's
Mm-hmm.
grains will be near the edge, they vibrated free,
Right.
whereas the smaller ones didn't, and they stayed captured.
Yeah.
And it happened in hard drives first, but then we start, it eventually would happen in any component. And that's when the lawyers got involved and we never saw any more about it. But we did the failure analysis and said, well, that's odd. Why is that happening?
Right. Right. Why is that happening? And these are kind of things, the fact that you're not that that's kind of not a common cause, but a special cause failure that the manufacturer one of the people in the chain of material suppliers was not aware the impact of to the others. And
Yeah.
epoxies, encapsulating epoxies are, of course, very highly protected secrets. They're usually proprietary because of the nature of getting the right mix for the
Hmm.
correct TCE. You talked about fire retardant and other things that have to go into
Or
it,
it
and
has to
then
seal too. It has
it
to
has a
actually
seal, right? And
actually
it
actually bond with the
seal.
component so it doesn't have
It has to
contamination
go
issues.
through a reflow of 185 C to 200 C,
Yeah.
and not melt and not be damaged, and expand and contract every time the power is turned on to the device at the same rate. But also underfill for BDAs is a
Hmm.
problem too.
Yeah. Yeah.
That's been mismatched where the TCEs where it was not expanding and contracting and eventually sheared some of the balls. So, there's just, of course, there's thousands of failure mechanisms or potential failure mechanisms in any circuit board, in any one of those tiers of suppliers in their chains of material suppliers in that. I don't know if the Nichicon bought their electrolytic formula from somebody else and then put it into or they developed it internally and just somebody messed up.
Well,
Didn't,
the story I heard was the guy that was blending the electrolytic solution
hmm
took vacation, and somebody else came in and wasn't aware that you're supposed to add this white powder until it turns
Yeah,
a particular color because they
right.
didn't have weights or anything else. The guy was just scooping it out of a barrel and pouring it in, stirring it until it was the right color.
Real precision there. Yep.
It was close enough that it worked.
Yeah.
Yet when
Well,
he
worked for
wasn't there,
years.
when he wasn't
Right.
there, somebody said, "Well, how much are I supposed to put in?" Well, put in enough. And
Right.
like when the
Don't,
chef tells you to add salt to
right.
taste, and they're like,
Yeah.
"Well, whose taste?"
Yeah. Just tell the guy the formula, don't write it down or have any precision measurements to it.
Well, there's a lot of processes like that
I
it's
know. And they work fine until somebody screws up
goes
and,
on or goes on vacation, doesn't
goes
tell
on
anybody.
vacation, right? And that happens all the time. So
Yeah,
that's the thing. I say to list all those failure mechanisms in a book in a
in a
class.
course or whatever.
Well, you just said one that you knew was terrible. So
Well, there's
I kind of
reasons
don't
for
know.
that.
We'd have to piece that apart. Why was it terrible and what were they doing? Because you can talk about electromigration. You can talk about
Talk about great
tin
visuals.
whisters, cracked solder joints, the delamination. The many things could happen just on a circuit board, much less motors, pumps,
Yeah.
mechanical systems. It's kind of like if you were to try and learn all those things, that could take years. And when you get into a company, a lot of those things are irrelevant because they're not dealing with those mechanisms like, pneumatic pistons closing a polyvinyl tube to
Yeah.
stop a flow. It's not,
If you're not using that, you don't need
you're
to know
not
those
using it. So,
mechanisms.
so to broadly go and try and learn all the failure mechanisms to me would be admirable, but unless you're teaching a college course or
Yeah,
some
teaching
general
a course, and even
course.
then, you're still going to just scratch the surface. Yet, I think
Yeah, exactly.
there's two parts to it. One is be aware that things fail in different ways, and here's at some
Oh,
level, just
yeah.
understanding what corrosion is and how's that different than wear, is the
Right,
baseline. You got to start somewhere. And
right,
then there's interesting ones that give you clear signals that you can measure, like the one that database is talking about. You can measure metals in your lubricant. And that metal's got to
right,
come from someplace. It's
right.
not coming from the lubricant. So
I think, and these are all the things that could lead to better prognostics and health monitoring, which is a big, relatively new,
relatively new for us, it's new.
for
But it's
relatively new approach to monitoring and for products and components that wear out, like uh,
gears.
IBGTs, right?
Yeah. Oh yeah, IGBTs. Yeah.
Yeah, they're a power device used in a lot of course, wind generators,
Well, anything
inverters,
from
and
AC to DC or
right, right.
DC to AC, I should say.
So those have wear out mechanisms, and they do fail before the product's technological obsolescence because of solar panels and wind generators are supposed to last what 20 years,
Yeah, yeah, that's what they,
something like that.
yeah.
So they know this, and that's there's getting more work in predicting the known wear out failure mechanisms.
But then somebody goes out and takes a shotgun and shoots them up, and then they're like, "Well, we didn't expect that failure
Yeah,
mechanism."
right. And I know that those guys out there in the world of failure analysis said, wow, when they've opened up a case of something, is a wow, how did
Yeah.
that bugs, how
How
did
did that
that,
rat get in there? I saw
right,
that once.
right. We thought we had a small enough grill that it wouldn't be able to crawl through, but those are kind of things you just those are kind of learned from experience, and it's many times very product specific.
Oh, I'm sure it is, but I'm thinking there's got to be a way to help folks come up the speed quicker. And so we'll talk again about it someday, but
Okay.
it's I've got a few ideas. And this database I saw, at least for the factory equipment type stuff, look pretty slick. I really like it. So hopefully we get more folks to get a chance to check that out.
Yeah.
But
And it's great to
so
see anything about,
yeah.
giving you a starter for at
So if
least what
anybody,
to
if
look at.
you, let's ask our audience though, if you're listening to this and have some ideas of, how do you come up to speed quicker on identifying failure mechanisms so that you know what the next steps are to deal with it. I'm all ears. And I think Kirk, you'd be interested in it too, because or even better is if you have a really cool failure mechanism you've learned
Yeah.
about, we'd
Yeah.
love to hear the story of it
Right.
and
Tell
share
me
it with
one
our audience.
that's was not expected and really surprised you, and you've never seen it before.
Yep. And as there's always a story, and we don't have to name names or industries or whatever, but enough details so we get an idea what the mechanism. That'd be way
Right.
cool. So anyway, you can get a hold of us at accendoreliability.com/go/SOR. And you can also get a hold of Kirk or I and the other hosts of the show through LinkedIn or our About pages. So there's plenty of ways to get in touch. And hopefully one of those 3 or 4 different paths will work. So, although this morning I was checking out failure mechanisms on an email system, and that's a whole different world. We didn't even talk about software.
Yeah, exactly. There's another one that, another input that
Another
can fail,
10,000
that can
ways it
cause
can fail.
2,000 ways it can fail. So,
Yeah. Why does anything work? That's the real mystery for me.
well, it is. It's amazing that it does work. And when my wife gets mad at something failing technologically, I say, but you really enjoyed it when it was working, and it was really helpful to you when it was working. And you're glad that the engineers made that and designed that for you most of the time. Now that you become dependent on it, you're really mad.
That's right. So you got a good product when that happens. But
Yeah.
anyway, so good talking to you, Kirk.
Yeah, we'll talk again soon.
Yeah, cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.